Welcome to the Offshore Engineer Meet the Experts debate, coming to you from Aberdeen and the Offshore Europe exhibition and conference. This is one of two debates we're bringing you with GL Noble Denton. Now, GL Noble Denton, part of the GL Group, is an independent technical advisor to the oil and gas industry. GL Noble Denton have a presence in more than 80 countries and a team of nearly 4,000 engineers and scientists with a strong presence here in Aberdeen. We're here for a discussion and Q&A on understanding the various requirements and global best practices for maximising performance and efficiencies across the life cycle of a floating production system. FPSOs, as I say, that's floating production, storage and offloading vessels, have historically been used in the North Sea, and as investment in the region grows, there remains an active FPSO market. Extreme weather conditions and the proliferation of smaller marginal fields lends itself to the use of FPSOs. Indeed, today there are more than 200 global FPSO installations. In this debate, we're talking about understanding the technical, environmental and regulatory aspects, and I'm joined by four leading experts in the field. So please welcome our guests today: Ian Fraser, Martin Brown, Bolshoy Bhattacharya and Adrian Goodwin. Now, I have several questions about floating production, and during today's programme we'll also be taking questions from the audience. But first of all, let's hear from each of our guests who will set the scene for us. And let's start with Dr. Ian Fraser, who will be talking to us about functional requirements for FPSOs, key drivers to consider during the early concept stages. Ian has more than 30 years' experience in the offshore oil and gas industry, particularly in the field of pipelines, risers, moorings and offshore installation, working in the UK and Norway. And he's currently a course speaker in the Informa FPSO training series and is the General Manager for Maritime Applications for GL Noble Denton. Here is Dr. Ian Fraser.
Thanks. Just to kick things off, I want to cover some of the basic aspects of FPSOs. As you see, functional requirements for FPSOs. What I want to cover is where they fit into a field development and what the basic requirements are for an FPSO. Here's a typical example of an FPSO. I think when it comes to field development, it's one aspect of a field development. With FPSOs, they fit pretty much exclusively with subsea wells, where you have a field development over a large area where you need subsea wells to drain the reservoir and to improve production. You can link these back through flow lines and risers up to the FPSO. Or if you have a very relatively small field life, you can use the FPSO. You can bring it on to the field, extract the oil from the reservoir. When you're finished, move it on to another development. I'd like to define some of the major components of an FPSO. I think we've been talking about FPSO, but nobody's defined it. It stands for floating, production, storage, and offloading. You can see the ship here. The major components of the production unit are the storage unit for storing the oil as it comes up from the reservoir. There is a turret which allows the vessel to weather vane. This is particularly used in the North Sea, where you have weather coming from all different directions. That allows the ship to turn around as the weather direction changes. The turret is connected to the mooring system, and Martin will be talking more about mooring systems after me. And the oil is flowing through a set of risers up through the turret onto the production deck, which includes all the production facilities, the utility facilities for generating power, and also the accommodation. The oil, once it's ready for export, is often transferred onto shuttle tankers, as you see there, through a floating hose at the stern of the FPSO normally mounted on a reel. So what I want to do now is to deal with questions that Paul and the audience are going to put to us relating to the functional requirements of an FPSO, how you physically define that in an early phase of a field development.
Okay, well, we'll come to the questions at the end. So
Okay.
if you take a seat
Okay.
now. Thank you very much, Ian. We'll come back to Ian with questions at the end of the presentation. So thank you, Ian. Our next subject is integrity assessments of moorings for floating production systems. And to tell us more about that, let's meet Martin Brown. Martin, thank you for joining us.
Thank you. Okay, just to clarify, there are quite a number of different types of mooring systems for floating production systems. Ian mentioned that we can have units that weather vane around a turret, but we can also have simpler systems for environments where the wave direction doesn't change much. So you can have it spread moored with mooring lines coming up at the bow and the stern. And there's various designs for the terminations of the mooring lines when they come up, and then we also have the flexible risers on a turret that will tend to come up in the centre. But if you are a spread moored unit, you'll be able to bring up the risers on one side of the unit. So a simpler system, a spread moored system, but it depends on the environment whether it is suitable. Sorry. Now, people who are not particularly familiar with the industry don't necessarily appreciate how heavy some of the components are, what hassle it is to install them. This is an individual chain link, and that weighs something like 450 kilograms. So you can imagine when you've got thousands of links, just the dead weight of the line itself is very significant. We also typically use spiral strand wire. And this is, again, for a long length, a major deployment operation. And then you typically will be connecting up chain to spiral strand wire. And that, again, you need craneage to insert shackle pins, etc. And the actual termination on the seabed may well have drag embedment anchors or driven piles or suction anchors. You need to understand that the mooring system actually has a tough job over a long period of time. It's a mechanical system, and most mechanical systems deteriorate over time, and the same happens with mooring systems. But the difficulty we have is that, say, towards the end of a 20-year life, you still need to be able to withstand a 100-year return condition storm. So it's a hard job, and also because you're in one location, you cannot weather route to get away from the worst environment. So you are forced to ride out whatever comes your way. The schematic gives you a flavour of what some of the mechanisms that act on a mooring system. There's two areas that have a particularly hard life, and that's the hang-off where it attaches to the floating unit, and also the touchdown area. You have bending and tension and sometimes torsion acting in these areas, possibly out-of-plane bending. And then you also have corrosion occurring throughout the system. It's a seawater, it's a harsh environment. And then you may have a harsh seabed. So if you've got a gravelly seabed, you'll get potentially damage at the seabed. Now, the mooring system is absolutely fundamental. It's a safety critical element to make sure that the FPSO stays on station. And if, for example, a mooring line fails, the FPSO can come off station. If you lose a number of mooring lines, ultimately you can do serious damage to the subsea infrastructure. And this little picture here shows what's happened there. Now, the actual environments, particularly in the North Sea, that you can see are extremely severe. You can see, this is something like a maximum wave of something like 100 feet that's coming through. So it's really harsh environment, and you're sitting there for year after year having to take whatever comes through. Things do deteriorate in service. You can see on these two slides, these are extreme cases, but you do see where there's significant rotation. You also have corrosion acting, and we've also started to see in certain locations sulfate-reducing bacteria and biofilms developing that can actually result in speeded up corrosion. A bit like you can sort of see corrosion pitting from sulfate-reducing bacteria. This can actually happen on mooring chains as well. The implications are such that lines can fail and at times have failed. These are examples of spiral strand wire that has become damaged. On this case, an area where there's been regular bending of the wire plus corrosion, and eventually it overloads. And then these flexible risers, these high-tech products, very expensive. Eventually, if you pull on them enough, they can end up in this sort of condition. So this is absolutely worst case scenario, and a great deal of our effort goes to try and prevent anything like that happening. But it must be stressed, there are hundreds of float production units out there, and it's very rare that you have a serious incident. You may have a single line failure, and the systems are actually designed to have a single line failure. But it's also interesting that lessons a little bit get lost in history. This is the infamous Brent Spar buoy, infamous because of the Greenpeace when it was dismantled. But it actually had a very good design of connection to the hull, and it was a very successful mooring design for 19 years. But some of those details now seem to have got a little lost in time. But hopefully, we can move forward from successful lessons. What we've tried to do from some of the problems that we've seen is improve how we design and look after mooring systems, and this is where there's a mooring integrity guidance. There's a second draft that we've been working for Oil and Gas UK, and that is actually now just about to go out to industry consultation. But we believe this process will enable us to improve the long-term durability, because what needs to be perceived is that if you lose mooring integrity, you're potentially shut down. And we've got this little MIG and the MIG jet engine just so that you can make it a bit snappier and think of these things. So really, I hope we haven't got long, but just to give you a flavour of how these mooring systems need to operate, some of the things that potentially can go wrong, and how we can avoid those sorts of problems. Thanks very much.
And our next speaker is Bolshoy Bhattacharya. Bolshoy is a proponent of safety and reliability at sea through incident-free dynamic operations in floating production, based at GL Noble Denton Aberdeen, providing FMEA, gap analysis, trials development and incident investigation services. For the last year and a half, Bolshoy has been employed as a control systems engineer specialising in automation and control, and he's previously worked in shipping, giving the experience on FPSOs he requires. Ladies and gentlemen, Bolshoy Bhattacharya.
Thank you, Paul. Good afternoon, everyone. Just following up after what Martin told you about mooring, the other aspect of it is dynamic positioning. Dynamic positioning is a way of maintaining station by using your thruster forces to counteract the environment. For dynamic positioning vessels, we provide a service which consists of FMEAs, gap analysis, trials, etc. The FMEA is one of the most important aspects of it. It stands for failure modes and effect analysis. So what we do during this process is identify all the failures which can happen in the DP system, identify the effects, and analyze what will be the end consequences of having such a failure. Why is it required for dynamically positioned vessels? Well, it is a regulatory requirement for vessels which are classed dynamic positioning 2 and up. But even for a DP1 vessel, an FMEA can give a good perspective of what can happen if a failure occurs. Advantages of a well-produced FMEA. Now, FMEA there are various standards all throughout the industry, but a well-produced FMEA can provide insight on future incidents, can provide insight on how the system works, and it can be a decision support tool for the crew to work from. The end goal of the FMEA is to provide incident-free DPU operations. The consequences of an incident are vast, monetary, environmental, and the FMEA should be able to at least predict what would be the consequences. For the FMEA process, we have got elements and the process. The elements basically, it's DP2, detection, protection, and performance. So we want to detect any failures which can happen. We want to protect against those failures happening, and we want to ensure that the equipment on board is capable of providing the performance it's supposed to. And to achieve those elements, we have the key processes, which is predict, prove, and protect. This is the sort of motto we follow to provide those elements.